Dr. Benny, how do we know that a chemical reaction is at equilibrium? You ask a very good question, Benjamin. Well, one way we might do is to consider what happens during the course of a chemical reaction and measure the amount of products it produces. Let's examine the decomposition of dinitrogen tetroxide into nitrogen dioxide on how this might occur. Dinitrogen tetroxide is a colorless gas, and the nitrogen dioxide is a reddish-brown gas. Let's imagine that initially we start with dinitrogen tetroxide, which is a colorless gas. As time goes on, what did you observe in the container, and what could you conclude? I see that the brown color is getting darker and darker in the container. This suggests that dinitrogen tetroxide decomposes into nitrogen dioxide. Good observation and interpretation, Benjamin. At some points, we cannot observe the color change anymore. Let's imagine that we measure the concentration of dinitrogen tetroxide and nitrogen dioxide as a function of time. In this particular reaction, we are starting off with only dinitrogen tetroxide, and we know as the reaction proceeds, dinitrogen tetroxide decomposes and yields nitrogen dioxide. However, the concentration of dinitrogen tetroxide does not decrease to zero, and the concentration of nitrogen dioxide does not continue to increase. Although initially the amount of reactant and the product changes rapidly, they both plateau at some level at these later times. So, this is when the reaction reaches chemical equilibrium, and the amount of reactants and products do not change. The concentrations of reactants and products do not necessarily have to be the same, and in fact, they are usually not the same. What must be happening in the reaction so that the amount of reactant and product remain the same? Since the concentrations of reactants and products remain constant, it suggests that the rate of decomposition from dinitrogen tetroxide to nitrogen dioxide equals the rate of the reverse reaction from nitrogen dioxide to dinitrogen tetroxide. Correct, Benjamin. In other words, on a molecular level, some dinitrogen tetroxide molecules decompose into nitrogen dioxide at the same rate that nitrogen dioxide molecules recombine to form dinitrogen tetroxide. This is why we are going to use the term dynamic equilibrium, because the word dynamic means change, but the word equilibrium means equal. A juggling act would be a good analogy to illustrate the dynamic aspect of chemical equilibrium. In this video, each person is throwing and catching clubs at the same rate, and each holds an approximately constant number of clubs. In addition, the individual clubs are changing locations among the jugglers. To recap, a chemical reaction at equilibrium is dynamic on the molecular level, but no further net macroscopic change is observed because the rate of the forward reaction is equal to the rate of the reverse reaction. when we have a reaction that is at dynamic equilibrium, we use this equilibrium arrow to represent that a reactant is being converted to a product and the product is being converted back to the reactant.